Hi, I'm Dr. BCMR. Mutations are inevitable, and every life system tries to undo the damages. And mutations start off with usually as DNA damage, and then they establish as mutations, and which may have consequences, many of them drastic and a few beneficial. In the end, it is all about DNA, the base pairing between the nitrogenous bases, and it is intricately linked with DNA replication. We'll have a look at some of the ways how mutations get established. The simplest one is that the replication errors. DNA polymerase is a very efficient enzyme. It has certain degree of accuracy. It makes one mistake about 10,000 or 1 lakh bases per 1 lakh bases added or so. And because it has proofreading exonuclease activity, 3' to 5' exonuclease activity. And still, there are sometimes mutations or a wrong base could be incorporated. And that wrong base is usually it happens as a as a mismatch. And this mismatch, if it is not detected by the repair systems and one of the bases is removed, or the adenine is not removed, here in this case adenine is wrongly added where guanine should have been added by DNA polymerase, and so we have a mismatch. And if replication happens prior to the repair mechanisms can do something about the adenine, then in the next round of replication we may have thymine added, and now this is no longer a mismatch repair, and then there is no way repair mechanisms would see this as a DNA damage or anything. And so what was a GC base pair is now an AT base pair in one of the progeny at least, and that is a mutation is established. And if we try to describe in terms of mutations, it is a transition event. It is a point mutation. Transition because a purine is replaced by a purine, guanine substituted by adenine. So those are replication errors. And there are as we discussed with the different types of DNA damages that could happen. Something like oxidation could have happened on the guanine, and that oxidation of guanine, for example, oxo-G, can base pair with C cytosine as well as with adenine. So if there was a guanine which is oxidized, and then we have replication has occurred, and then if it is in a different tautomeric form, then it will base pair with adenine, and adenine gets incorporated here. And if the next round of replication does occur, then it is going to become against the thymine. Against adenine, a thymine is incorporated, and now this is not a mismatch, or there is no DNA damage, even nothing like oxidation either, and this is going to get established as a mutation. And that is how oxidation of a base, for example, could cause mispairing, and mispairing would eventually result in the establishment of a mutation. And there are many others similar ones that would have similar effects. Say, for example, tautomers. Tautomers are kind of alternate structures to normal nitrogenous bases. We'll have a focus on this one. This is an imino form. We have a cytosine, and it is supposed to be NH2 here, an amino group there, but because of tautomerism, which is everything is same except the way these atoms are arranged, and here the bonds is N double bond H, which is a imino group, so it is an imino form. So this cytosine, which is, these kinds of tautomers are usually rare. Amino form is normally the normal one, and imino is the rare form. So because of these changes, the base pairing activities or specificities change. Say for example, cytosine normally would have base paired with guanine with 3 base hydrogen bonds. But then here, because when it is in imino form, it can base pair with adenine as well. Similarly, every other nitrogenous base that we know, say for example thymine, in it is enol form, the opposite normal would have been the keto form. Enol form would base pair with guanine. Normally thymine would have base paired with adenine. Similarly, tautomeric form, enol tautomeric form of guanine base pairs with thymine, and adenine imino form of adenine can base pair with cytosine. I hope we can appreciate that when this base pairing changes, or when this base pairing changes, the sequence is going to change, because all of molecular or all of biological information, at least the fundamental biological information in the form of genome, is based on sequences of the nitrogenous bases, and these sequences of nitrogenous bases are dependent on the base pairing, because during propagation base pairing becomes very essential to allow the inheritance of the information from one generation to the other. Say for example, we have a tautomeric form of cytosine, as is depicted here, the imino form, and the cytosine is, this is the, assume the parent DNA, and now replication has happened, and through semi-conservative replication one of the daughter DNA molecules is fine, whereas the other one, in this imino form of cytosine, it can base pair with adenine. So we have a wrong base incorporated there because of the tautomeric form of cytosine. And if replication did occur prior to anything could have been changed or repaired, then the adenine that has been incorporated could get, when it is replicated, the lower strand will get incorporation of thymine on the opposite side, base pairing, and now a mutation has been established. What was CG is now a TA, that is a transition mutation, because cytosine pyrimidine is replaced with another pyrimidine. So these are some of the problems that can be because of the way hydrogen bonding is affected. It could be either because of any additions like oxidation, for example, or it could be because of tautomeric forms. Not just these, there are many other ways how hydrogen base pairing, the base pairing between the bases could be affected. There are compounds called as base analogs. As the name suggests, they look very similar to that of nitrogenous bases. Here is 5-bromouridine. As thymine is 5-methyl uracil. So basically the difference between uracil and thymine is just that thymine has a methyl group in the 5th position, whereas in this case, base analog, there is bromine in the 5th position. So it looks very much similar to that of thymine, and it could get incorporated into the DNA. So again, the 5-bromouridine, we'll just call it that, can be in enol form or keto form. So if we see this is supposed to be a keto form, that is double bond O, but then it is in OH, that is, it is present in enol form, because of which it base pairs with guanine with 3 hydrogen bonds. Normally thymine would have base paired with adenine with 2 hydrogen bonds, but in enol form of bromouridine, it base pairs with guanine. Let's see how it could change it. This would have been the normal keto form of the 5-bromouridine. So we have a sequence which is having incorporated bromouridine in the keto state. So keto is still base pairs with adenine, and that's kind of normal in a way. at least, in the way it base pairs. If bromoiodine has changed to the rare enol form, then and replication did occur, and in that case it will base pair with guanine, and now we have what should have been an adenine. Here we have an incorporation of guanine, and that is all right in a way, but what we will see here is that, so we have the TA, which is the normal one, that is 5-methyl uracil, whereas in this case we have the G incorporated, and when that undergoes replication we will have the establishment of G and C would have been it is a mutation. What was supposed to be a TA is now a CG, that is again a transition mutation. And in this case, in the bromoiodine, we just, for the illustration purpose, we assume that it is a keto, and in that case it will base pair with adenine. The point is that replication, the base pairing affects the way polymerase replication happens, and replication depends on the timing, and then many of the DNA damages could establish as mutations. So we have one another, it's not always, there is one another molecule or types of molecules which are mutagens. All these molecules that have the capacity to induce mutations are called as mutagens. And these mutagens in humans or wherever relevant could cause cancers. So they can be carcinogens as well. All carcinogens are mutagens. Somehow they have to meddle with the genetic material. Not all mutagens cause cancers though, but their probability could be very high. Here we are looking at something called as intercalating agents. We have looked at something like Yttrium bromide, how it stacks between the bases. Similarly, we have another example here. We are taking it as proflavin. Yttrium bromide is one of the, Yttrium is one of the other example. Acridine orange is another example. What is common with all of these is they have a planar structure with 3 rings such as shown here. These structures are kind of plane and hydrophobic, so they can slide between the bases as shown here like this. So assume this is one base, this is the another, and these are the 2 other bases. And the intercalating agents slide between them and they stack along with the bases. That is called as, those are molecules that do so are called, referred to as intercalating agents. They stack between the bases. There is a problem because of them. And how do they result in mutations is what we will try to have a look at. So the template, assume we'll have a template here and there is a primer. And if we have something like an intercalating agent that has occupied this space, assume this is where the polymerization should be occurring. And if that, and here we have one intercalating agent stuck or base stacked along between T and A. Now if DNA polymerase is adding something, say in this case we'll just take it as this, so against T, A is added, and here we have an intercalating agent because of which some base could be added which could base pair there probably. And then A, against A there is T, GC, CG and TA. And if the bottom strand, I mean in the next round of replication, if the bottom strand is replicated too, what we will see is we will have, and this is cytosine that was added against an intercalating agent, and now we have, because it is when it is being polymerized in the next round, we will have an addition of extra G there. So the intercalating agents can cause insertions within the reading frames. If it happens, then there will be a serious consequences on the reading frame and the protein that is going to be produced, like in the frame shift mutations. Not just insertions, they can also allow or make deletions happen. Say for example, this is the template and here is the primer, like we have already discussed above. And then if there was a intercalating agent within the primer, and then that might read off one of the bases here, and that means it will say for example we had CTA, and against this T one of the intercalating agents could read it as such, but the base that is marking the phosphodiester bond would be G and T and CGA. And if that means one less base has been added in there. GA should have been there, but G and then T, A is missing. And if replication did happen of the lower strand, at least from the lower strand, we would see that one of the A is missing here, or AT is missing. That is how it can result in deletion. So the same or very similar way of things can also happen. It's not that DNA polymerase or all mutations are because of the faults of or stabilities of the nitrogenous bases, or induced because of chemicals like base analogs or intercalating agents. There could also be something like slippage. This is another kind of replication error that could be because of DNA polymerase. Here we have a template and this is the primer. Assume that replication is happening, and what you notice is it is completely made of C, and the bottom template is complementary, the bottom primer is or the growing strand is G, obviously. And the primer and template, they are bound here, but they may sometimes come and bind here like this. So the primer can bind here, or sometimes the template can loop. Here I'm showing an example or representing the primer looping. So these two, there were 5 G's, guanines, and they looped and they base paired here. The G, this G, third G, the G here, fifth G should have been base pairing with this C, cytosine, but now it is base pairing here. Sequence compatibility is there, complementarity is there, so they will base pair. And DNA polymerase will just keep adding other C's. So as a result, what we see is that there are extra 2 G's that were added, or 2 bases in general, and that is how slippage of the primer could result in the insertion. Deletions can also occur because of slippage, and that is if the template slips. During replication, if the template forms a loop like this, then the growing complementary strand would have 2 bases less, or base pairs less, and that is because of this looping here, and that causes in deletion. I hope we can appreciate that the mutations, all that occur, are intricately or mostly dependent on 2 aspects. One of it is about the base pairing changes. Changes could occur because of natural tautomerism that is existing, or it could be because of base analogs or intercalating agents. It can also be because of mistakes that are done by DNA polymerase. Mismatches could happen. There is always a probability of that. And then slippage of either the template or the primer can also occur. I hope you understood the ways mutations get established. See you next time. Thank you very much.